Hi, everyone.
Hey, Dario. So something about Dario. Dario is a lecturer at the Department of Computing at Imperial College London since the fall in 2020. Something about him. So he received the Bachelor of Science and Master of Science in Aerospace Engineering from the University of Padova, and a Master of Science in Mathematical Modeling and Computation from the Technical University of Denmark. Then he actually obtained a PhD here at ETH from the Automatic Control Lab, and he then moved to some better weather, especially these days, to do a postdoc in Santa Barbara. And then he joined the Imperial College. In general, his interests are at the interface between game theory and control theory, and his focus is on the design of behavior influencing mechanisms for socio-technical systems. He has won several awards for his work, and I think today's talk is very exciting. The title is Two Birds with One Stone, Optimal Approximation for Integral Routing and Congestion Pricing. And I think Dario will give us an introduction and some insights about this exciting research topic. So Dario, without further ado, go ahead, the stage is yours.
Thank you, thanks, Joelle. Let me just double check that you can in fact see the screen. Oh, good. Okay, welcome everyone. Thanks, Joelle, and everyone from the committee for having me today. The work I present is joined together with Martin, a colleague from the University of Liverpool. As you can see from the title, in the talk, I will go through two related but different problems. The first problem I'm interested in is in approximating integral routing, and the second problem is that of congestion pricing. Let me briefly introduce these two problems. So in integral routing, we are given a road traffic network. Typically, we are given a pair of origin destinations, and we are given a fleet which we would like to route from origin to destination. The goal here is that to route the fleet in such a way to minimize the congestion endogenously generated by the very same fleet. On the other hand, when we think about congestion pricing, the setup is similar. However, we do not have complete control over the fleet. Instead, cars are thought to be self-interested decision makers, and we can instead utilize congestion pricing in the form of tolls to steer their behavior, again, with the objective of minimizing congestion. So the goal is the same: can we minimize congestion? But in one case, we do not have complete control in the congestion pricing setting, whereby in the case of integral routing, we do. And what I claim, what I hope to convince you with this talk is that both these problems can be solved through a common framework, which will be what I present in the rest of the presentation. I'd like to start with some quick introduction. I believe all of you are familiar with pictures like this. As a matter of fact, congestion is soaring these days, not just in the UK and in Europe, but throughout the world. Not just congestion, but also the costs associated to congestion. So I'm thinking about the number of hours spent on the road. In the UK, this corresponds to 1% of the GDP, but also to indirect costs. For example, the amount of noxious pollutant. In the UK, transportation is the largest producer with 27% of such share. Now, this is obviously a global problem. It's a socio-technical problem. And as a matter of fact, a number of solutions are being developed to tackle these problems from different angles. I'm highlighting here only a few. This is by no means an exhaustive slide. There's clearly one of the main drivers being electrification, another one being tighter integration between public transport and different modes of transport. But two areas where I would really like to focus on today are those two you can see here at the bottom. So autonomous mobility on demand and congestion pricing. So let's zoom, first of all, in autonomous mobility on demand and briefly highlight what is the main idea there. So in autonomous mobility on demand, we're given a network, we're given a number of customers which appear with a corresponding origin and destination, and we completely control a centralized fleet which needs to route these customers along this network from their corresponding origin to their corresponding destination. One typical objective here is that of minimizing congestion, as typically minimizing congestion is correlated to maximizing revenue or to maximizing profit for the actual mobility platform. So again, the key ingredients here are we have complete control over the fleets and we are trying to minimize congestion. Now, on the other hand, congestion pricing is a similar problem, but with an extra twist. So congestion pricing is extremely hyped these days because a number of cities have been rolling out or are planning to be rolling out their own congestion pricing scheme. The overarching goal is again the same, meaning that from the standpoint of the transportation authority, we would like to minimize congestion. but we do not have control over the decisions of each and every driver. But what we can put in place are instead incentives or indirect mechanisms to steer their behavior. And so the question here is, can we design incentives, in particular congestion pricing, so tolls over each and every edge of the network, in order to, again, achieve the same goal? So if we put them one on the side of the other, in the case of AMOD routing, we have centralized control, and the goal is that of routing a fleet to minimize congestion. On the other hand, if we think about congestion pricing, we again care about minimizing congestion, but we do not have complete control. As a matter of fact, we want to utilize interventions in the form of tolls so as to reduce the corresponding inefficiency or improve the performance, minimize the congestion. So I'd like to highlight that both of these problems are extremely challenging. And why is it so? Because I will be looking at the case where there is a natural integral constraint to the problem, meaning that the cars need to be routed on one single path from their origin to their destination, and we do not take a flow approach as typical in the literature. So we cannot take a car, cut it in half, and send it on different paths. We really have one car, that car needs to go on one specific path. This is the main reasons for which the problem on the left is challenging. The problem on the right is challenging for two reasons. First of all, we have an integrality constraint, and in addition to that, we do not even have control over the cars. So can we indirectly achieve good performances? These are the two problems that I would like to tackle in the rest of this presentation. So I'll summarize what is the main idea, and then I'll stop for a second to see if there are questions regarding the overarching structure of the presentation. So the problem I care about is that of minimizing total congestion in integral routing. And I will be looking at two cases, the case where we have complete control and the case where we don't have complete control of the vehicles. Throughout the presentation, I will essentially settle this problem entirely, and I will present two results to do so. The first result sets the stage for what cannot be achieved, meaning I will show that minimizing total congestion is a difficult problem, meaning it is NP hard to approximate below a certain threshold, which I will provide in the presentation. So this means that we cannot hope to get a polynomial time algorithm, meaning an efficient algorithm, to obtain an exactly optimal solution, not even an approximate solution, unless our approximation is worse than this factorial. On the other hand, though, one then asks the question of what can then be achieved in polynomial time. And quite surprisingly, at least from my point of view, our second result shows that when congestion pricing is judiciously designed, then the performance we can achieve in polynomial time precisely matches the approximability factor that I presented before. And this gives rise to the first known algorithm, to the best of my knowledge, to solve this problem with an optimal approximation. I'll stop here. Joel, if there is any question from the audience, feel free to let me know. Otherwise, I'll move on.
No question so far.
Okay, great. Then let me start with the first main result, which I would like to discuss together with you. So we would like to set the boundaries for what cannot be achieved in polynomial time. So let me just discuss what is the setting that we are working with. So let me introduce the model. In our model, we're given a set of resources which we can think of as the edges in an underlying network. For example, the roads. Each and every resource is associated to a cost function, or more precisely, a latency function. This latency function tells us, as a function of the congestion level on that resource, how much is the travel time. So if 3 agents were to be on this edge, then our congestion would be L1 of 3. If there were 5 agents, this would be L1 of 5, and so on and so forth. This is typically a non-negative increasing and oftentimes convex function. Think about a polynomial, for example. And we have one such latency function for each and every edge. We are then given a set of agents. Here I'm thinking about the centralized setting. So I depict these cars as being all red. They are all centrally owned. And each agent is given a pair of origin destinations, which means that every agent has a set of possible paths that are the feasible choices for this agent, which will allow this agent to move from their origin to their corresponding destination. In this case, for this car, there are 2 possible simple paths. In this other simple case, there is one and only one simple path for the other car. Then each and every agent perceives a cost, which is the travel time along their route. And this cost is made up simply by summing the travel time of each and every of the components of this path. So for example, if we go back to this representation here and we think about this path, we just need to sum up the latency function of this edge, this edge, this edge, and this edge to compute the travel time for the dashed line. So this gives cost to the agents whenever all agents have selected their own path. And what we care about here is minimizing system cost, where the system cost is the total congestion or the total travel time, meaning the sum of every agent's travel time. So think about focusing on the peak hour, for example, in the morning, when everyone goes from home to the office. The system cost here represents the time that everyone spent on the network. So sum up everyone's time. This would be 2,356 hours. That's exactly what this quantity is. And we care about minimizing this very quantity. So I would like to remark that if one was to look at the continuous version of this problem, meaning the problem whereby cars are allowed to be cut in half, in thirds, in fractions, then this problem can be tackled much more easily because it can be reformulated under very mild assumptions as a convex optimization problem. And there's been a lot of work from a number of scientists, both in the list of speakers, I would imagine also in the audience as well. And we have a short list here of some of the more recent work within this area. Instead, if we look at the case when flows are integral, meaning we cannot cut cars in halves, then the problem is open, meaning it is unclear what can be achieved and what is a good polynomial time algorithm and what are the inherent computational limitations. I would like here to precisely focus on this question for the time being. So let me provide you with some background in terms of what are the existing results. There is plenty, but I would only focus on two main results. So I will call mean SC the computational problem of minimizing the social cost. So the problem I presented just a second ago. So this problem was shown to be NP-hard about 10 years ago, the exact problem, meaning it was shown that we cannot compute an exact solution in polynomial time unless p is equal to. More recently, it has been shown that even in a benign setting, meaning even if all latencies are linear, so a very simplified setting, the problem remains NP-hard. Although very much less is known in regards to how hard is it to approximate this problem. So these results are for the exact solution. How about approximation results? The only known results, to the best of my knowledge, is the following, which is implicit result in a way. So it focuses only to the case of polynomial congestion games, meaning the case where the latency functions are polynomials. And in this case, we know that minimizing the social cost is NP-hard to approximate within a factor that you see here for some beta. But this is just an existential result in the sense that it doesn't give us a concrete value of beta. This just gives us an idea of how this quantity grows with the degree d, because beta is independent on d. But it doesn't tell us, if we look at linear latency function, then we get square root of beta, but we don't know what beta to plug in, right? So it's an implicit result in a way. It gives us an asymptotic performance, but we don't know what the NP-hardness boundary is. So overall, what I would like to highlight here is that certainly there is no tight computational lower bound. I would say that there also is no computational lower bound at all, in that this is not really a concrete computational lower bound that we can utilize. Contrary to that, our first result completely settles this question and provides the tightest possible approximability result. So I'll state the claim here in the simplest possible setting, but the claim does generalize. In particular, I look at the case when we are given a certain network, we are given origin destination, we are given latency functions, and all latencies are identical, okay? And they are identical and equal to some function which I call b. The result will generalize. So in this case, I claim that computing an allocation that minimizes the social cost is NP-hard to approximate within a factor smaller than this seemingly daunting expression. So what does this expression tell us? So first of all, notice that this is in a way a well-defined expression in that we are trying to maximize this quantity here over x being a natural number. And the numerator is nothing but the expected value of the denominator according to a Poisson random variable. So this expression here is a function of x. We are trying to maximize this expression over x. We are taking the worst case over x here in a way. And this will give us an approximability factor for that specific class of latency function which we have chosen. Now, it might seem daunting, but it can be explicitly computed for a very large number of latency functions. So for example, we immediately learn that if we look at linear latencies, meaning we set this b of p to be exactly equal to p, then simply detailing this result for the case of linear latencies tells us that it is NP hard to minimize the social cost below a threshold of 2, where this 2 simply arises by computing the expected value of p to the power of 2. This is the second moment of a Poisson random variable, which you have explicitly written here, and maximizing this expression amounts to evaluating it at x equal to 1, because then the expression decreases. So effectively, what we have learned is that, we actually know what we cannot ever hope to achieve for linear latencies, but we can obviously go beyond that because we have a general expression. As I said, the result trivially generalizes to the case when latencies are different. And what one needs to do in there is to look at the worst case approximation ratio or hardness result produced by each and every latency considered separately. Now, as a result of this, one obtains the following corollary, meaning if we instantiate this hardness result for general latency functions, then the hardness factor would be exactly equal. One can prove this to the d plus first Bell number. This is a well-known number that arises in combinatorics. So, for example, for linear latencies, we recall the result I presented before. So it would be NP hard below a threshold of 2. When we look at quadratic latencies, this would be NP hard to a threshold below 5, and so on and so forth. Now, this seems to be telling us that there is very little hope to compute a good approximation to this class of problems. And why is it the case? Well, it is the case because typically in the literature, latency functions are polynomials of high degree. So for those that are familiar with BPR functions, these are typically polynomials of 4th order degree. And the Bell number here grows very quickly as the degree grows. So one should expect no hope to compute a good approximation. However, that's not the case. And why is it not the case? Well, because for real-world instances, latency functions of the form BPR do have more properties, meaning that typically the linear coefficient here, the coefficient multiplying the 4th power is much, much smaller than the coefficient BR. This essentially represents the fact that there is the free flow travel time, meaning BR, the amount of time we would spend on the network where no car was there, has a more significant impact on the overall travel time than the congestion, meaning if congestion increases by a little, the travel time increases by much less than that. So effectively, AR is much, much smaller than BR. So what one can do in these settings is that one can perform a more refined analysis as opposed to this sort of coarse analysis here. And one can observe that the actual hardness boundary does depend on the ratio between these two numbers, meaning how large are one with respect to each other. And what it turns out is that in real-world networks, and here I'm depicting a number of real-world networks taken from this commonly utilized set of networks, these real-world networks are such that the ratio between AR and BR is very small, almost close to 0. So here, what does this mean? Well, this means I'm showing here in black the NP hardness result obtained by sort of a more specialized analysis, which I'm not showing. So this plot tells us that, for example, if we take the Austin network, our result says that it is NP hard to approximate a solution below an approximation factor, which is essentially 1. Right? A little bit worse for Anaheim, a little bit worse for Chicago, 1.2 for Berlin, and so on. So this gives some hope that for real-world instances, we can actually compute a good approximation. And the reason for which I'm raising this point is that later on, I would provide a polynomial time algorithm whose performance precisely matches the hardness factor. So if this hardness factor was to be bad on real instances, we wouldn't care about these algorithms, right? But it turns out that we do care because the approximation factor that we can get will match this hardness factor, which is reasonably close to 1, in my opinion. Okay, so I'll very briefly highlight what are the proofs idea on how one goes to prove the previous result. So we need to prove hardness of some problem, which means that we will be starting from some known NP hard problem and reducing that problem to congestion gains. And we do that introducing a gadget, which we call partitioning system, which is an object which we will utilize to induce precisely this hardness factor that we need, 2, 5, the Bell number, and more generally that expression. So again, I'm going to be very, very high level here, but I would really highlight what are the ingredients. So the problem we reduce from, meaning the originally difficult problem, is called gap label cover and appeared in a number of famous results in the literature, particularly the original work by Feige. So in this problem, we are given a bipartite graph, meaning a graph divided in left and right nodes, and we are given a set of colors, say red and blue. And we are also given a set of constraints, one constraint for each and every edge. And these constraints tell us over the edges how we should color the right node once we have chosen the color for the left node if we want to satisfy the constraint. So in particular, this constraint over this edge is telling us that if we were to choose red as a color for the left node, if we want to satisfy the constraint, we need to choose blue for the right node. Okay? Instead, if we were to choose blue in here, we need to choose blue on the right if we want to satisfy this constraint. Our task is then that of coloring the nodes in order to satisfy as many constraints as we can. Now, the original NP-hardness proof here goes, the original NP-hardness statement is the following, again, very informal. It is NP-hard to distinguish between a yes and a no instance of this problem, where a yes instance is an instance where we can find a coloring that satisfies all and every possible constraints, as you can see here. While a no instance is an instance where we cannot find coloring that satisfy even a very, very small fraction of the number of constraints. Okay, so these essentially are two extremes. Either we can satisfy all constraints or we can satisfy almost none. And the original claim by Fay is that it's NP-hard to distinguish between these two problems. Now we will build atop this, and we will utilize this to construct a congestion game of which we want to prove hardness. And to induce the right hardness barrier, meaning this factor rho, we will utilize a partitioning system, which is defined as follows. We are given a set of resources. Again, think about the edges, for example, and every resource will have a constant cost, which is equal to the latency function. Then we construct this matrix here, where we think about the columns as being the players in our game, and we think about the rows as the possible selection in terms of allocation for each and every player. So essentially what is in each and every of these boxes is just a subset. So these are just subsets of the sets of the resources. So in here, there are some resources, resource 1, 2, 27. Here there is 3, 4, 28, and so on. Now this object is constructed so as to have a very important property, meaning if all agents were to coordinate themselves and choose one row in terms of their allocation, then this would correspond to a very low social cost, a very low congestion. On the other hand, if they coordinate themselves on this scrambled allocation, where no two agents select resources on the same row, then this will incur a very high cost. How high? Well, the ratio is as high as such that the ratio between these two expressions precisely matches the hardness result that we want to achieve, the hardness factor that we want to achieve. So at the end of the day, one would then be reducing from this problem. The yes instance, which is the good instance, would be made correspond to this case here when we achieve a low cost. The no instance would be made correspond to this bad case here. And if at that point one would then be able to solve the minimum social cost below a factor rho, one would then be able to distinguish between a yes and a no instance of an NP-hard problem, which will then complete our proof. If you're interested in the details, I'll suggest you take a look at the manuscript or reach out to me on this specific point. Okay, hopefully this was clear, at least in terms of the general idea and the general result. The general result being, hey, look, this is the best we can hope to achieve in polynomial time. Then the second part of the talk, we'll talk about actually how we can precisely match that hardness boundary. Can we design an algorithm whose performance is as good as what we could hope for in the best case scenario? And the answer is yes, and we can do so through the design of taxation mechanisms. Again, the setup is exactly identical to what I presented before. Now, the only difference is that agents are now self-interested. So we do not have control over the entire fleet of vehicles, but agents are self-interested and they care about minimizing their own travel time from origin to destination. So for those that are familiar with the terminology, this is a standard network congestion game, and in particular, the atomic version, meaning the case where, again, we cannot split cars in half. Now, in this setting, we know that equilibrium allocations, meaning allocations where no agents can choose a different path and reduce their cost, we know that these allocations are inefficient, meaning that if we look at this quantity here being the ratio between the system cost at the equilibrium allocation and the system cost at the optimal allocation, this quantity will be strictly larger than 1. This is termed price of anarchy, as it represents how inefficient self-interested decision-making is in this specific setting. Now, our task as the central designer is, all right, we would like to put in place tolls, one toll for each and every edge, potentially tolls being congestion dependent, And by introducing these tolls, we would like to reshape the set of equilibria, so much so that the resulting equilibria would have lower system cost, as low as we possibly can. So we are trying to influence the worst case equilibrium and reduce this inefficiency level, which is also called, as I said before, price of anarchy. Now, I would like to highlight that if we were able to achieve good price of anarchy, meaning if we could put in place tolls that reduce the price of anarchy to an approximation factor equal to the hardness result I presented before, then we can also immediately get a polynomial time algorithm. Why is that the case? Well, because price of anarchy is exactly the ratio of the performance that we care about, and because equilibria, not all, but correlated equilibria, for example, can be computed in polynomial time. So much so that if we have good price of anarchy, one simply to utilize any such polynomial time algorithm to compute an equilibrium, and this equilibrium would have a performance matching the price of anarchy. This and a number of other motivations spurred the question of designing tolls to try and minimize the price of anarchy, and there is significant work in the literature. This is just a limited extract of some of the more related work to what I'll be talking about. Overall, though, there is no matching approximation, meaning that I'm not aware of tolls design whose price of anarchy matches the hardness factor I presented a second. Again, contrary to that, our work completely settles this second question, meaning we will be able to design taxis whose price of anarchy and therefore whose performance precisely match the hardness factor. So here is the second statement. I'll again state this in a simplified setting, but the result does generalize with a little bit of work this time. So we consider the case of selfish integral routing, as we've seen before, and I'm going to be focusing in the case where all latencies are equal. This is the reason for which I'm saying that it's a simplified setting here. And we take standard assumptions such that the latencies are positive, they represent travel time, they are non-decreasing, so the more congestion, the more expensive it is, and they are semi-complex. So what I claim is that no matter what small of an epsilon you give me, I can always compute a congestion pricing mechanism so that its corresponding price of anarchy is upper bounded by this hardness factor I presented before, 2, 5, and so on, plus epsilon. Again, this epsilon can be made arbitrarily small. Now, this extends to the case where latencies are different, but I'm not going to go in there as it requires a little bit of work. But also, as I highlighted before, this immediately gives us a very powerful result in that this corollary tells us that since we can achieve good price of anarchy and computing equilibrium is easy, we can then easily compute good allocations with an approximation factor matching this quantity that I presented before. I'll briefly walk you through what is the mechanical idea behind how one computes one such approximation, and then I conclude. So the original problem was that of minimizing the social cost. And again, here we had integral constraints, meaning we had to route each and every car over one single path. What we do is that instead we look at a relaxation, at a continuous relaxation of this original problem. And we look at this relaxation which arises by taking the expected value of the original cost function, expected with respect to a post-random variable. What we do then is that we solve this continuous relaxation, and interestingly, this continuous relaxation is a convex optimization problem. So this can be solved to epsilon optimality very efficiently in polynomial time. So we call V star the arg minimizer of this problem, meaning the set of loads, the set of the congestion over each and every load, over each and every edge. And we then utilize this optimal congestion level over each and every edge to construct tolls. And we construct tolls by essentially evaluating some explicitly given function, which I'm not writing here, but which is given in the paper. Think about this as a black box. This black box takes some set of parameters, these parameters V star, which are the congestion level in this optimal problem, and gives returns toll. Now, what I claim is that these tolls here defined in this way will have that performance that I want to achieve and which I claimed before. I'd like to specialize this just in the case of linear latencies to really showcase how this reduces to something concrete and tractable. So if we have linear latency functions, as we've seen, this Poisson expected value is nothing but the squared of the congestion plus the congestion. This is a convex function. So we just need to minimize this. We need to find routes which are now continuous in the sense that we look at a continuous relaxation that minimize this cost here and take customers from origin to destination. We get the corresponding V star, meaning the congestion level over each and every road. And then the modified latencies are nothing but the original latency function where we add some toll, where the toll is nothing but the slope of the latency times this optimal factor. Okay, so in conclusion, what have we looked at? We've looked at two related but different problems. The first problem being we would like to minimize congestion, we would like to route cars from origin to destination, we have integrality constraints, and we have complete control over the behavior of the vehicles. On the right-hand side, instead, the problem is identical. We again want to minimize congestion, although we do not have complete control, and we want to utilize interventions in the forms of taxation mechanisms, tolls, congestion pricing, they are all the same, in order to minimize, again, congestion and indirectly influence the behavior of the agents. What I showed is that, first of all, I set the boundaries for what cannot be achieved in polynomial time. This was the first result. And then as a second result, I showed that, interestingly, through the design of taxation mechanism, we can actually achieve a performance that matches the inapproximability factor. And this is true not only for the case on the left-hand side, but for the case on the right-hand side, as our design was based on the use of taxation mechanism and on the notion of equilibrium allocation. A few remarks. I find interesting the fact that if one looks at competitive decision-making and design incentives in the best possible way, the resulting performance precisely matches what could be achieved with the centralized, from a centralized perspective. I also find it surprising that taxes are sufficient, meaning taxes are typically a very coarse way of incentivizing behavior, in the sense that they do not distinguish between different players' identities. Players taking the same route will have the same tax no matter, regardless of their identity. Finally, what I would like to point out is that the approach I presented here requires the solution of a centralized convex optimization problem, which might be undesirable. So one can get away only with local computation, meaning without essentially any information at all regarding the origin destination of the customers, at the price of losing a little bit of performance. So one goes, for example, from an approximation factor of 2 for linear latencies to an approximation factor of 2.01. When one moves from the centralized approach I presented today to a local design approach, which you can find in this manuscript here. Having said so, I'd like to conclude, and perhaps let me summarize the manuscript, the result of the manuscript with this sentence here. What we've shown is that judicially designed taxes do achieve optimal approximation, and there is no other tractable intervention that can improve upon this result, as our result matches the hardness factor. You can find claims to substantiate what I discussed today in these two manuscripts, in particular in the first one here regarding the general approach and the convex optimization problem I presented, and the second one for the taxes based on local information. I'd like to thank you, and I'm more than happy to take questions.
Thank you, Dario, for the great talk, and also beautiful way to finish it with this sentence here. So we have some questions from the audience, and I will ask them one after the other. I think the first one is the following: is somebody was asking in the beginning of the talk, if the continuous problem is easy, can we not just use it to get a good approximation in the case in which we have a lot of players? So what is your comment?
This is a very good question. So the answer is yes and no. It really depends for the setup that you're looking at. So in particular, what I presented today applies obviously to routing through traffic networks, but it also applies to a number of other problems more generally, right? What I presented today is essentially mathematical results in terms of this class of problem is hard or not hard, or what can be achieved. So for traffic routing, the answer is yes, you could do that, but in principle, you would not be guaranteed a certain performance guarantee. Or in other words, I could cook up a very bad instance where no matter what you do, if you utilize the continuous approximation of the problem, you would end up with a bad approximation. Now, you could argue that in practice, this might not happen, and I could also agree with that. So I think it's a matter of, would you like to have performance guarantees ahead of time, or would you like to just roll with what you have and see what the ultimate performance is? Also, what I would like to highlight here is, though, that if one tries to implement this, and we've done so for AMOD type of systems, the performance does indeed turn out to be slightly better than what one could do for real-world instances if one utilizes a continuous approximation and some form of rounding at the very end.
Thank you. I think this answers completely the question. I think another interesting one that comes from the audience is that you made this claim that it's cool to see that taxes work without knowing the identities of the players. And somebody's asking, would that claim still hold if different people, different players would experience different costs while using the same link? So if you have personal costs.
Yes, so I think this is a very good question, and I believe the answer to that question is no, meaning that if you were to take this approach and utilize it in a setting whereby costs are perceived differently, then what I presented would not work. And the idea being that effectively the reason for which taxes are player agnostic is precisely the fact that agent perceives cost in the same way. There could be ways to tweak this so that it does also apply to the case where players have perceived cost in a different way. But that's a separate work.
Okay. Then somebody is wondering, how does this tax scheme relate to the famous VCRI optimal toll scheme? So the one where we do tolling by the marginal cost.
Okay, very good question. So the question is, in the continuous version of the problem, it is known that the marginal cost tolls achieves optimal performance, meaning that if we utilize marginal cost tolls, the price of anarchy will reduce to 1, meaning we were able to obtain the optimal approximation. Interestingly enough, that result, which holds for the continuous version of the problem, does not hold for the integral version of the problem. So that is the main difference. And maybe even more interesting is the fact that if we try and utilize the discretized version of marginal cost tolls for this problem here, the price of anarchy, meaning the inefficiency level, would get worse even than that achieved by not pointing any toll. So in other words, in the discrete setting, if you utilize marginal cost toll, it's bad. You do worse than doing nothing, at least from a worst case point of view.
Okay, very interesting. And the final question that was from the audience is that, so at some point you mentioned that these congestion functions like the BPR are a threat because of the fact that you have this x to the 4 factor, but in reality, you also made this observation of this first factor being very, very small, considerably smaller than the second one, right? But then somebody's asking, isn't that in the case making the problem a bit trivial, meaning you don't have really strong congestion? So, I mean, what's your comment about that?
Yeah. So everything needs to. The answer is ni, in the sense that that is in a way not necessarily making the problem trivial, right? Because if you have a lot of cars, meaning there's a large flow, and this coefficient is small, it doesn't mean that, it could still be that the overall congestion builds up to a point where this large flow cancels out this small coefficient, right? So the fact that that coefficient is small simply physically represents the fact that if you add one car to the system, then the travel time would increase by little. But if you add a lot of cars, that as you could be doing, right, the travel time, the congestion level, the congested travel time could still increase significantly. So I see the point that is being raised, but I don't think that it is trivial in a way. Okay, very cool. Maybe I have a final question, which is more related maybe to the next research. Sometimes we chat, me and you, we discuss these things. How do you see now the integration of multiple providers? So essentially now you presented 2 layers, like the taxation layer and the reaction layer. What if you put competition also in between, where you have providers competing, reacting to the taxes and making experience the taxes to the citizens? Extremely good question. I think it's a very interesting direction to go into. We have started to look into that, but not for the setting I presented today, meaning that already in the case when you have continuous flows, that problem becomes difficult because essentially when you have competition between different providers, you have a game that these different providers play, and then at the bottom level you have some form of customer's response. Now, even this game, even the simplest possible setting you can write down, and I'm sure Joy, you're familiar with that, turns out to be a difficult game to analyze, in the sense that you typically have some form of convexity properties, but you don't have monotonicity property, which is typically a property that you need to find to guarantee existence, uniqueness of equilibrium, and good algorithms. So in one-liner, I think it is very interesting. I think it's very hard in the integral setting. I think it's definitely something we should be looking at in the case of continuous flows, but it's still challenging also in that setup.
Very cool, thank you. So it doesn't seem you have other questions. So I would thank you, Dario, again for the great talk, also the great overview for new people on this subject.